Good evening, am I audible?
Yes, ma'am, you are audible.
Evening, ma'am.
Okay, let's wait for 2 3 minutes more, then we'll start.
What? What will you start?
We'll just wait for a few more minutes for other people to join, then we'll start with week 9.
Nine. And ma'am, what to do for OPP? Like any suggestion? What to do?
That we will discuss in the OPE sessions. Okay, there will be separate session. 2 sessions before OPE we'll have just for the programming part.
Okay. Okay, ma'am.
Okay, so the attendance is really low in this class. I don't know why, but yeah. So if you or whoever is present here, if you have a way of communicating with your classmates, then please let them know that not to miss this last 4 week sessions, okay? Because the end term weightage is going to be 50 to 55% from these last 4 weeks, and these are pretty difficult. Uh, like if we compare what we have done till now, okay? So just let them know. Try to increase the attendance every term. Usually these last 4 weeks have the highest attendance. So okay. Anyways, so this is the first session after quiz 2, I think. So any feedback from your side?
Very easy it was,
Right,
except for one question that was minimum number of relation to make BCNF, but I did that.
right. So if you have any doubts in any questions, or like if your answers are not matching with the answer key, something, so you can let us know on discourse, okay? Like a few people have already let us know. So two of the questions we are reevaluating. So one question was there from week 8, I think it was the magnetic disk question, where it was a NAT type question where the answer was given as 11.
Yeah, it was 11.
Yes. So if you calculate it in the straightforward way, then the answer will come as 11 only. But one student, he calculated in a different way, so he approximated up to two decimal places, and that's why his answer came as 10. So for that one question, since his method is not totally wrong, although it could be done in a simpler way, but we have reevaluated that. So the answer for that is, now we have put a range from 10 to 11.
And
Okay.
what was another?
What was his method, ma'am, if I may ask?
Yeah, you can check his discourse post. Okay, so
Yeah,
he
ma'am.
has,
I can share it here in the chat
yeah,
box.
so you can just share the link. So he has given his entire method how he solved it. It's not wrong, but there was no need for that approximation since the numbers were pretty straightforward. They're canceling out, right? But
So,
yeah, for that we
he,
have reevaluated. So if anyone has given any answer from 10 to 11 in this range, so we will consider that as correct.
so did he use 1000 instead of 1020? Something like that.
I don't exactly remember. You can just share the link. You can check it out on discourses method. So I have also posted the solution for it. We can compare both. Okay. And yeah, regarding OP, so can anyone tell me what's the date given to you?
30th March में.
30.
30th March. Right. So 10 days left. So within these 10 days only, we will be planning two OP sessions. So one will be basically just on that week 2 and week 3 SQL content. Okay. Because in your OP exam, you'll have 7 questions in total, right? So that is from the SQL part, and then you will also have two different questions from that Python database connectivity part. So the first session that we have will be on the SQL revision session. Second, we'll have one session dedicated to just the Python DB connection. Okay. But for Python DB question, I hope we all have gone through the grading documents. So you'll know that solving that Python DB question is mandatory to pass the OP, and overall you have to score a 40%. Right. So the breakdown is like in the 7 questions that are purely from SQL, there are going to be 3 questions of easy level, 3 of medium level, and one difficult level question. Okay. So if you have access to past OP papers, then you can go through them once. Otherwise, we'll discuss PYQs only in that revision session. All right. So
So that
week
will be when,
9,
ma'am?
that will be scheduled possibly next week only, both the sessions.
Okay.
Yeah.
So we'll come to know that those specific sessions
Yeah,
are
we'll
going.
send out announcements.
Ma'am,
Okay.
I have a suggestion.
Yeah.
Can we have those calls early in the week so that
Yes, we're
we will
planning that
have
only. Like
time to study?
Within Wednesday, we're planning to take at least one session.
The Python DB connectivity session with the Python questions, PYQs. If we can do that first, that will be really helpful. Thank
Yes.
you.
Okay. So Python DB part, I'll just say something. If you have seen the actual week 7 session that I took this term, so that is basically what all you need to know for the OP also, right? So we'll just practice some different problems. But okay, I'll try to schedule that before.
The
Like,
reason I'm asking is some of the I'm not sure whether they are the PYQs or I'm not sure, but one or two questions that I've come across that talks about Python DB connectivity. They have some Python coding as well that's
yeah, some
required.
string manipulations this might be required.
Yes, I think some people are struggling with that. So, till what level of complexity will that be? And will
See,
there be any easy and tough question in Python DB connectivity so that we have a choice between that?
yeah, there will be 2 questions. Okay. So you'll have to solve one of them. And
Okay.
I think that that is given in the grading document, like how many you have to solve in total. As far as I know, that there will be 2 options from which you have to choose one. But the thing is, in this Python DB question, our objective is not to test Python knowledge. Okay, so it won't be very complex, the Python coding part. Mainly, you just have to write the SQL query. So there are a few questions where there is no manipulation in Python code. Okay, just the SQL query. In some other questions, the output might be in a specific format. So you have to make sure that the string is manipulated in that way. Okay, so we'll discuss all of those questions in the OP session.
Thank you, ma'am.
Ma'am, will we receive any practice sets?
I think mock will be released. One mock should be released.
Mock for OPP.
OP, yeah, might be.
Okay.
Okay, so in SQL session, just practice whatever we did in week 2 and week 3. So some more advanced problems I have created, so I will discuss those also. All right. So for now, let's focus on week 9. So week 9 is mainly about your indexing, right? And so lot of topics are there. So starting from now on, let me tell you, week 9, 10, 11, 12. Let's not take 12 into account. 9, 10, 11. These three are very content heavy. Okay, so there's a lot of things we have to learn in a short time. So today I will discuss indexing. So if you have gone through the lectures or the slides, you know that there's a part about binary search tree, B tree, B plus tree. That is how indices are implemented, right? So that part is relatively easier than hashing. Okay. So hashing, you will know that there are 2 types of hashing that we have to study, static and dynamic. So static is still pretty straightforward, but dynamic hashing can be a bit challenging. Okay. Even though we don't ask a lot of questions from dynamic hashing, but still in PYQs you can find questions on that. So I have decided that today I am going to start with indexing, the basics. Okay, and then we will move on to the hashing part. So the B tree, B plus tree part, I will ask the instructor to cover in the next session. Is that okay with everyone?
Okay, ma'am.
Okay. If we have time, then I can give you a brief on those two. Okay, let me share the screen. Is it visible?
Yes, it's visible.
Okay. So first of all, anyone would like to tell me what is an index? Why do we need it?
Index gives random access.
Okay. Yeah, that's one point. So index in a database. Why do we need index in a database? It's just like you ask the same question, why do we have index in a book? Right? Every book has an index, that which chapter is in which page number. So that it's easier to access that particular chapter. So in just one go you can search where it is in the book. You don't have to go through the entire book. So that the same concept is used here also, that since a database can contain a lot of data, a lot of number of tuples, so if you are looking for a particular tuple, it's not possible to go through the entire database every time. So if we have an index, then we can just look in that index and look up where that tuple is present. So in an index, it is also a index file. It has two separate entities in it. Okay, so every entry in the index file can be broken into two parts. The first part is the key part. Okay, so every index has a key. What is the key? It is nothing but based on what you want to search. Okay, say if I have a database which is a student database, let's say I have data about the student ID, roll number, name, address, all of this. So if I want to build an index on this database, then I have to choose an attribute to act as my key. Okay, that based on this attribute, I will search. So I can make that as the ID. ID can be the attribute. And the second part of the index entry is actually the pointer. Okay, that will show you where that entry is stored in the actual database. So for example, see this. So this table faculty is our database. Imagine that it is a relation in our database and we want to build an index on it. So an index on a table can be built in multiple ways. You can pick any attribute that you think is suitable for a key. Okay, but there is something called a primary index in which we use the primary key in the actual table as the attribute. So in this table faculty, what entries do we have? We have a record number, right? And a name and a phone number. So here, if we want to create an index based on the name attribute, so this is that index, this one. So here, see, the index table has two separate attributes per entry, right? One is the key part, that is name. One is the pointer part. So if I want to search, let's say, where is Pavitra Mitra, right? If I want to know what is his phone number, I just know his name. I want to know what is his phone number. So I can just look in this index, find out where is Pavitra Mitra here. So corresponding pointer is 6. So this will point you to the actual place where this entry is stored in the database, and from there you can gain all the information about this particular person. Similarly, if we want to build an index based on the phone number, so let's say I have the phone number 81664 and I want to know who this phone number belongs to. So same thing you will do, just look up what information you have. With that, you look up in the index that, okay, I have this phone number, let's look up where this phone number is present in the index. So you find it in the first row. Then what is the corresponding pointer? It is showing row 6. So you just go to the corresponding database row 6 and you find that name. Okay. So like this, a table obviously will have multiple attributes. So based on any suitable attribute, you can build an index. So this is the basic structure. Okay. Now index mechanisms index is used, why we just understood that it is used to speed up the access, because in a large database, if you have an index, you can directly access an entry. So search key, that is the first part of an index entry. It is the attribute or set of attributes used to look up records in a file. The search key can be one attribute or it can be a set of attributes that we use to actually look up the records. So in the example that we just saw, the search keys were name and phone number. So an index file consists of records, right? Index entries, where each entry is the form, search key, and pointer. Okay, this is kind of like a linked list, you can say. It's not actually a linked list, it's the structure of a node, or like the structure of a node in a linked list is like what? Data part, link part. So similarly here, each entry works as a node. Okay, so each entry has a search key and a pointer. But the entries are not linked together like a linked list. Okay, I'm just making a comparison. So index files are typically much smaller than the original file because they're just storing very limited data, right? So there are two basic types of indices. One is your ordered indices, where search keys are stored in sorted order. It can be alphabetical order, numeric order, whatever. It is stored in a sorted order. So those are ordered indices. The second thing is hash indices. So in hash indices, the search keys are distributed uniformly across buckets using a hash function. So this part we will discuss when we go to hashing. For now, just focus on this ordered indices part. Okay. So
Can you explain
okay, this
search
is
key
not
again?
needed. Yeah. See, in this example, if I want to build an index on this table faculty based on the attribute name, so name becomes my search key, and the corresponding pointer will show where that name is stored in the actual database. Okay, so any attribute that you find suitable can be your search key. Basically, in this index table, every record is of the form that every record means every tuple, every row. It is of the form that there will be a search key part and there will be a pointer part. So the search key part is the actual attribute that you have taken from the original table, which will help you locate the desired record in the table. So like here I have taken name as my search key. I can also take phone number as my search key, but the pointer is necessary. Okay, so every entry will have two parts, search key, pointer. So name can be a pointer, phone number can be a pointer, any suitable attribute can be a pointer. I'm sorry, it can be a search key. Pointer is where it points to the actual record in the database. Like here, see, every record in this faculty table has a record number associated with it, which can be thought of as its primary key also, right? Or here, name can also be a primary key, since in this particular table we can see that there are all unique names present. Anyway, so each record has some number associated with it, 1 2 3 4 5 6 7, like this. Now in the index table, whether you form it on name attribute or phone attribute, that's your choice. The corresponding pointer for every search key value should be accurate. Like see, in the first entry, Anupam Basu, this is the search key, right? So let's say you are looking up, you want to know what is the phone number of Anupam Basu, but you don't want to search in the actual database because it's too huge. So you just search in the index that is formed based on the name attribute. So in the index you search where is Anupam Basu stored here. What is the corresponding pointer to? Now,
Ma'am,
yeah.
I have a question. Like this index table, this will be having same number of records as the original table or not?
So it will have the same number of records based on what attribute you are choosing, right? So here, since look, we have to choose such an attribute which can uniquely identify a tuple, right?
Okay.
So if my original table, let's say it has 100 rows, if this faculty table has 100 rows, my index, if I form it on the primary key, here let's take name as the primary key, then index table will also have 100 rows. Okay, but there are different types of indexing. So this is just a basic like structure of indexing, but when we learn the different types, what is sparse indexing, what is dense indexing, so based on that the index size will change.
And
Okay.
one thing like if like this is looking same, so what's the point of making it? We can also like if in the database structure we
No,
can have
this
something.
is a very simple example, but in real life scenarios, an actual database relation will have a lot of attributes. Here you can just see the faculty table as name and phone number attributes. It might have a salary, department, different attributes in the same table. So that in the main table, each record is carrying a lot of data. So it takes a lot of storage to store that whole thing. Whereas in the index table, you just have one attribute, which is the search key.
Okay,
So you just have to store that. Yeah.
reducing load on
Index size
memory.
index size is always going to be less than the actual table size. Okay, that's the
Okay.
whole point. So we don't have to search among that huge amount of data, we'll just search the index.
Like, ma'am, so it's just reducing the load on memory. Storage, it doesn't have that much effect.
It is just reducing our access time.
Yeah, okay.
Okay. You have to allocate some extra storage for the index. Right.
Yeah,
So that is the trade-off here. Obviously, some trade-off is going to be there. So yeah, if the case is such that we have 100 rows in the actual table and in the index we are doing, let's say, primary indexing. So the primary key is the search key. The primary key of the actual table is the search key in the index. So in that case, obviously 100 rows means 100 unique primary key values. So the index will also have 100 entries, right? If it is a dense index, that we will learn later what is dense and what is sparse. But for this example, if there are 100 unique names of faculties, then there will be 100 unique entries in the index table also, but still the access time will be less. Now see, what is important here is this part. Okay, so an ordered index is what, where index entries are stored sorted on the search key value. For example, author. Okay, so the if I make an author index based on the author name as the search key, in that case, if it is an ordered index, then the author name will be sorted in alphabetical order. Okay, and what is a primary index? Just what the name suggests, that in an ordered file, the index whose search key specifies the sequential order of the file. That means we will be using the primary key, okay, in most cases, but it's not necessary that you have to use the primary key. The main thing in a primary index is what, that the order of the actual file and the order of the index file, okay, these two sequential orders are the same. So in a sequentially ordered file, the index whose search key specifies the sequential order of the file. So I'll give an example that will make it easier to understand. But a primary index is also called clustering index. Okay, this, there can be MCQs from here. What is a clustering index? What non-clustering index is your secondary index. So in an index, what we
So, ma'am,
understood is we will, yeah,
uh, so it means whether index is primary or secondary, uh, it makes sense to talk about it only if the file is already in sequentially order. If file
file
itself
is in
is
some, file is always going to be in some sequence, right? In some order. Now, if the
okay,
if the index actually, okay, the index actually has a search key which specifies the sequential order of the file. Okay, that means both are in same order, same sequential order. Then it
okay,
is a primary index. But
okay.
secondary index is when your actual index specifies a different order from the actual file. That is secondary.
So can we say, let's say, name is a primary key. My
Hmm.
file is ordered on the name,
Hmm.
and I choose name as the faculty name as the primary index also. Search
Yes.
key for primary index. Then we
Yeah.
can say faculty name is primary index. But
Yes. If both
file
of
is
them have the same sequential order.
okay, ma'am. But if I choose phone number as a index, whereas file was ordered as per name, then phone number becomes the secondary index.
Yes, because the order is going to be different.
Okay, ma'am.
Okay. So same order, if it's maintained, it's a primary index, but it doesn't necessarily have to be a primary key, which is the search key. Secondary index also, the only difference is that you can take any key as the search key, but the order will be different than the actual sequential order of the file. Okay, this is the main difference between primary and secondary index. So just understand these definitions. We actually, when we solve the problems, these things won't really matter much. Okay, just remember the definitions, what is secondary, what is primary index. An index sequential file is what? An ordered sequential file with a primary index. Okay, that
Ma'am,
means ordered sequential file means what? Where everything is sorted in that file. Right. The file is stored in a sorted order, either alphabetically or in some way, whatever is the, maybe we are maintaining the order with the primary key. Okay, some way it is a sorted file which has a primary index, then it becomes an index sequential file. Now, see, this
ma'am,
part is, yeah.
in the starting lectures, like in week one, professor said that in the storage, we don't have a fixed order for this tuple array. Like tuples don't have an arrangement, so which tuple will come first is kind of unpredictable there. So,
Where the,
where we are comparing.
yeah, go on, finish.
here, at which level we are saying that it is indexed and it should be in the sequence of primary.
Okay. So where is the relation actually stored? Where is the database stored?
Relation actually is stored in the storage drive, maybe a hard disk or a
Right.
SSD.
So the same places where we will store the index also. When we work with it, things will come into the main memory and all. But the actual schema of the database, it has three levels, right? So the
Mhm.
tuples and everything, where in which level does this belong?
Tuples belong to, I guess, logical level.
Right? So logical level. So there has to be some order that is maintained, right? In the schema. In the schema, there is some order in the logical level. Okay.
Okay.
When you go to the actual disk blocks, that I'm not talking
Hmm.
about the disk blocks. I'm just talking about the logical level of the schema. So there is
Okay.
some order in that. Okay. It might be stored in a different manner.
Hmm.
So the where how this is stored, that we will learn in the B tree B plus tree part. Okay. Then this will become clearer to you. Okay,
Okay.
exactly how we maintain the order. So there are pointers, record pointers, block pointers for that, how we
Hmm.
maintain the order of that. Okay.
Okay.
Now, in indexing, this thing is something which is very important, dense and sparse indexing. So lots of questions has come from this part. So please understand this very carefully. A dense index is what? If I have a table which has 10 rows, okay, 10 rows, I want to build an index on that, then the index will also have exactly 10 rows. That means every row in the index is pointing to a single row in the actual database. Like here in this example, see, as many entries in this table, that many entries in the index table. That means every entry in the index table is corresponding to one entry in the main table, right? This is dense indexing. Like here, this is a some instructor relation, and the index is built on ID attribute. Okay, so 10101 will lead to this entry. So there is some pointer here, obviously, that is leading to this entry. So this is dense index. Now, what is sparse index? Sparse index contains records for only some of the search key values. That means, see, if I have 10, if I have, let's say, 100 rows in my table. Okay. Now, in sparse index, we first divide the table into certain number of blocks. Okay, equal sized blocks. So if I have 100 entries in my table, let's say I break the table down into 10 blocks, each having 10 entries. Then the index table, if I am using sparse indexing, will only have 10 entries, each entry corresponding to the first entry of each block. Okay, see, I think this diagram will help. So like this, block 0, block 1, the table will be broken into blocks of data. Okay, equal sized blocks. Now, every block will have, like I said, for example, if table has 100 entries and I have 10 blocks, equal sized blocks, then one block obviously contains 10 records, right? Now, consider this as one block. So this contains 10 records. Now in sparse indexing, each index entry will just point to the first record in each block, the first record. After that, if I want to search, let's say this block contains some 10 records like this. Okay. Now I'm just putting some arbitrary information. Let's say this is 101, this is some search key. So this one maybe starts like this, 99, 100, 101. So basically we are trying to, wait, let me modify this a little. So 99 is the first entry in this block, right? So in the index table, only 99 will be present. Now, what if I'm looking for record 101? So first you have to find that, okay, which index entry is closest to this? So 99 is the closest index entry you're finding in the index table. So first we will start searching like this. Start with 99. Start with the first block. Okay. So you can only reach the first record using the index. After that, you have to do a linear search through the entire block. Then again, you can go to the index table, go to the second block, first record of second block. Again, search the entire second block with a linear search. So this obviously takes a good amount of time, more than a dense index. Okay, because this linear searching is involved. Whereas in dense index, every record has its own pointer, own entry in the index table. But in sparse indexing, the index size reduces, right? So that's the good thing, that index size is small. So it doesn't take much storage, but the searching time increases. So for this index, tell me how many index entries should be in the index if it's sparse indexing on a table of 100 rows. I have a table that has
10.
100 rows.
10.
Correct.
10.
10
10.
entries, 10 blocks. For each block, one
Yeah.
entry which points to the first entry in that block. Right? So 10 entries. So this is dense and sparse index. This is the difference. Now, definition wise, if you study, it contains index records for only some search key values, like I said, applicable when records are sequentially ordered. Again, this sequential ordering is very important here. Okay, everything that we work with in this indexing part will consider that everything is sequentially ordered. Okay, we are only doing ordered indices. You saw in the beginning two types of indices we are working with: ordered and hash. Okay, so to locate a record with search key value k, so we have to find the index record with largest search key value that is less than k. So like I said, you find the nearest one. Okay, in this example, like I said, if I'm looking for 101, which is the nearest one that is less than this, 99 is the nearest one, so I start searching from here. Okay, so after that, once you reach the desired block where you want to, let's say I want to search 15151. Okay, this is the record that I want to search. So first in the index table, you see which one is nearer to this. Is this nearer or is this nearer? Obviously, I know that this 15151 entry falls somewhere between this first and second blocks, right? Just judging from the first, the search key value, since we know they're sequentially ordered. That means they're
Ma'am,
sorted. Yeah.
you said it is ordered and we take first entry. So instead of closest, we should check the lower bound of it.
Yeah, lower bound, obviously. See, how it
Hmm.
works is 15151 if I'm looking for. So just by looking at the index table, since we know everything is sorted, the search keys are sorted, that means it must fall somewhere between the first block and the second block. Now, which one is closer to 15151? 10101, right? Obviously, how does it work? 10101 will have entries that start from 10101 and then go on increasing. 32343 is the block which starts with 32343 and then increases. So obviously this will fall in the first block. We can say that much. So first
Uh,
you locate the first record.
okay. This 22222, it is in first block or second block?
This one is in first block. See, second block starts with this entry
Yeah.
32343.
Okay. So
Okay.
anything that greater than or
Yeah, anything that is greater than, if you directly find this entry 32343, then it's fine. If anything greater than this and lesser than 76766, that will fall in the second block.
Excuse me, ma'am.
Yeah.
Can't we do binary search instead of a linear search?
Now in database we always do linear searching because these records are not stored in that way. Okay.
Okay.
Actual storage is different. So you have to linearly search because see, the pointers are like, once you learn the b tree b plus tree storing part, then you'll understand binary search is not possible. You have to do a linear search here. So first, I mean, you know why binary search is not possible? You cannot find the middle element like that. See,
Okay.
for the
Yes.
same reason that in a linked list binary search is not possible, right?
Yes.
So if you do a linear search here, that will take some time. In worst case, it will take order of n times if each record contains n number of entries. If each block contains n number of entries, right? So if I am looking for 15151 in the index table, first I'll find which is the number which is closest to 15151 and less than this, obviously. So 10101 is that number. So we'll start with this block. Then you linearly will search until you reach this record. Okay. So this searching will take more time than dense searching. So in this one, see, I can directly locate 15151 and correspondingly go to the end entry. So this is a fixed constant amount of time it will take me, right? Whereas in this in this sparse indexing, you have to do searching twice. Once you're searching in the index table, once you're searching in an actual table. Okay, so anyone can tell me now just one or two differences between dense and sparse indexing that you understood till now?
Yes. So this dense indexing do a one to one mapping, one to one and kind of one to one and onto mapping. indexing to the record, and that sparse indexing do a block to index map. So it create a block of a particular size and map it to the index. I mean, index
So
to the block.
the kind of question that can come from here is like theoretical questions. If I say, it can come that okay, which type of indexing takes less time to access?
Dense index.
Dense
Dense.
indexing.
And which type of indexing takes more storage space? That is also
Dense
dense.
indexing.
Dense index.
Now, what is the other trade-off? That if you want less storage space but more access time, then you go to sparse indexing,
Hmm.
right? So these two types of indices are what is important. These are more important than your primary, secondary also, since I have seen more questions come from that part. Now let's discuss what are secondary indices. Okay. So this is
And
sort
what
of
is the difference between primary and secondary also let us know.
yes, primary and secondary. What did we discuss? The in primary, the sequential order of the file is maintained, whereas in a secondary index, the search key that we are using might not match the actual order of the file. Okay, so this is one.
What does it mean?
So the file is sorted in one particular order, but the search key you are using, it is not in that order in the index table. Okay, let's say in our actual table, it is sorted using this name attribute. Okay, but I am using phone number as my key, search key. Then these two orders will be different because phone number, if I sort it, it will give a different order than the actual table.
Okay.
Okay, so in secondary index, what happens? Index record points to a bucket that contains the pointers to all the actual records with that particular search key value. So there is a third, a medium between the index table and the main table. So secondary indices have to be dense. So how does this work? See, in this particular scenario, since this is secondary index, see, here the table is sorted on what? The ID. Okay, you can see it's in increasing order, right? Now the index is using what? It is using salary as the search key. This is also sorted, but are the orders same in both tables?
No.
So that's why it is a secondary index. Two have different sequential orders, both of
So
them.
in primary index, if it's sorted with ID, the search key also is ID itself.
Yes. So whatever is the sequential order of the file, that same order will be maintained in the index table also. So that's why mostly in primary indices, we try to use the primary key as the index search key. Okay.
What is happening to 80,000?
Yeah, I'll explain. See, here the search keys are salary. Okay, so starts with 40,000. So what is the definition saying? Index record points to a bucket first. So these are the buckets. Okay, these are the mediators. They contain the actual pointers to all the actual records in the actual table with the particular search key value. So we can see for 40,000, it is pointing to this bucket, which has the pointer to the actual record with the 40,000 salary, which is 15151. Okay. Now in 80,000, you can see in the actual table, how many people have 80,000 salary? This person
Two.
has, this
Two.
person has, right? That means two different pointers I need to store. So this bucket will have to store two different pointers. So see, every bucket is a single square. Here you can see it's a double square. This is one pointer, this is another pointer. So 80,000, this index table entry will store the pointer to the bucket. Okay. It will first point you to the bucket. In the bucket, you have to find out which entry you want to go to. Okay, so you can go to P1, which will lead you to the first 80,000 entry, which is this, and P2 will lead you to the second 80,000 entry.
So, will it be called sparse or dense?
This is a dense, right? This is dense indexing. See, for every record in the index table, we have a pointer, separate pointer bucket. So this is dense. For every record, one bucket. Secondary indices are always dense. Okay, there is no way that you can form a block here. But don't confuse this with multi-level indexing. Okay, that is a different thing. Secondary index uses a bucket to contain all the pointers to the actual records. Any doubt in this part? Secondary index, anyone didn't understand? Okay, then let's go to multi-level indexing. So this will take a little bit more time to understand. Okay, multi-level indexing means what? Index on top of an index. So the first outer level index will give you the pointer to the inner level index. Inner level index will give you the pointer to the actual table. Now there can be as many levels as you want. Okay, obviously it takes more storage, more access time, but in some cases it is necessary to have a multi-level index because the index tables become so large, right? So we just, to make them a possible size that we can store, we store them in a multi-level way. Okay, look, if primary index does not fit in memory, if the index file is so big that is it is not fitting in the memory, when you are trying to access something, right, whatever operation we want to perform in a computer, everything has to be done in the main memory, right, in the RAM. So first, when we do this search in the index, we have to bring that index into the main memory. So main memory is very costly and we don't have a lot of it, right, only a few GBs. So if the primary index that we have, when we bring it from the secondary storage into the main memory, if it doesn't fit in the main memory, then we cannot access. Then we have to access bit by bit, bring half of the table, then the later half of the table. So access becomes very expensive. So the solution to this is that treat the primary index kept on a disk as a sequential file. That means the index now becomes a table based on which we will form one more index on top of it. Okay, so obviously this is always going to be sparse because we are trying to reduce the size of the index. See, for example, I'll say if there is,
Yes, ma'am.
I think there is an example here. No, the multi-level index example I don't have. Okay, I'll just explain like this. See, this is the original database file. Okay, let's say this has some 1,000 records. Now, first level index that I built, let's call this level 1 index. So this is a dense index I formed. Okay, it has 1,000 entries as per this table, since it is dense. Now let's say I don't have the memory capacity to bring this entire L1 level index into the memory and do the searching. So what I can do is form another index on top of it, which will treat this as a table. Okay, so I will build one more index, which is a level 2 index. Now this index is going to be a sparse one because if we keep on making dense indices, then the size is not going to reduce. It will just remain same 1,000. But sparse index is going to reduce the size. So now this entry, this L1 level index table, if I want to make a sparse index out of it, let's break it down into 10 blocks again. Okay, for example, 10 blocks. So each block has 100 entries. Okay, so L2 index will have how many entries?
10.
10. So here there were 1,000 entries and drastically it changed to 10 entries here. So this level of index is now fit for us to bring into the main memory. So this will come into memory. We will search in the L2 level index first. Okay, and the pointer part will lead us to the L1 level index. So that way we don't have to bring the actual L1 level index into the memory. Okay, we'll just bring the smaller index. And then in the L1 level index, it is dense indexing, so you can directly reach the record in the main table. So multi-level indexing is done when the index becomes very big and it becomes very costly to work with that in the main memory. So then we just, to reduce the size of it, we build multiple layers of indices above it. Okay, so there can be 3 or 4 level of indices. You can find sums on multi-level indexing also in your practice assignments. Okay, is the concept clear, multi-level indexing?
Yes.
Okay, if you have any doubt, you can ask. See, outer index is a sparse index. Inner index is the primary index file. So inner index is our L1 index. So usually this can be a dense index. Okay. And the outer level index has to always be sparse to reduce the size. Now even outer
So,
index, yeah. Go
so
on.
ma'am, only purpose of having multi-level indices is to save storage.
To make it cost effective. Okay, because storage is going
Memory.
to, memory is, see, this is going to take memory, right? You are creating more index. That means more storage is required. On one table, previously we were creating one index. If you just create the L1 level index, so whatever memory that it's taking, now if you create L2 on top of it, it will take more storage. So storage is not the thing here. We are trying to reduce the cost, okay, because we have to bring the index into our memory in order to do the searching. Now if our L1 level index is so big that we cannot bring it into memory, That's why we need a sparse index, which is smaller in size. We can work with it.
Yes, ma'am. So I meant storage in main memory, not the real
Yeah, main memory.
backup
Yes,
in main memory.
exactly. Because main memory storage is expensive, right? We cannot have that much storage in main memory.
Okay.
So the outer level index will be a sparse one. Okay. And even outer level index, it can also happen sometimes. Let's say we are working with lakhs of records. In that case, even the first sparse index will be very big. So we'll create one more index on top of it, which is an L3 index. Again, one more sparse index for L2, or one more sparse index on top of L3. Okay. So these indices, as we build them on top of one another, as we go towards the outer indices like L3, L4, the size keeps on reducing, right? So we have to reduce the size until it becomes suitable to bring into the memory and work with it, and it's not that expensive. Okay, but indices at all levels must be updated. So if I actually perform some insertion in the actual table here, or some deletion, so the corresponding effect should be reflected in all the levels of index, L1, L2, L3, L4. Okay, otherwise it will become inconsistent. So multi-level indexing is a bit more complicated thing to implement, but yeah. So three types of indices should be clear to you by now. One is dense, one is sparse, one is multi-level. Right? Anyone has any doubt so far?
Ma'am, inner index. Can you explain it again?
Which one?
Inner index.
Inner index is this, the first index that we build on the actual table, L1. Okay, so if this is a dense index, then it will have exactly the same number of entries as the table itself. So this is the inner index. Anything we build on top of it is the outer index. Okay, so in a question, in a previous year question, it was, I saw that there are 4 levels of indices on a particular table, L1, L2, L3, L4. So L4 is the outermost level, L1 is the innermost level. Okay.
What is L2 then?
See, outermost and innermost we can say. L2 is what? It is outer to this inner level index L1, but inner to the outer level index L3. Okay. L2 is outer index for L1, but inner index for L3. So
So it is
L3 is built on L2. So the size of L2 is going to be less than that of L1, but greater than that of L3. Clear?
okay.
So yeah, these three types of
Ma'am,
indexing.
so
Now,
on a database table, we have facilities to index on multiple fields. Okay.
yes.
So does that mean we are creating independent indexes on
No,
each
no, no,
field,
no.
or it is multi-level only?
It is
When we say
multi-level, but on the same field. Okay. So if it is the search key value I'm using is the name per se. So this L1 table will have 100,000 entries for names. L2 will have 10 entries for names. But the search key you cannot change, right? If you change the key, then there is no way to access. All the levels of indices should be on the same key. Okay.
oh, oh,
If I do L2 on phone number and I do L1 on name, then how will you connect these two? Right? The search
understood.
key has to match. Okay. This part is not required, insertion deletion. From index, let's do the part where you will get the questions from. Okay, so the binary, see, balanced binary search trees, this part, I can do it now if you want, or you can do it in the next class, whatever you like. What should we do?
No.
Should we do it now?
Yes.
Okay, fine. But then one thing will be that I don't know if the next class whoever takes, if they will cover the dynamic hatching part or not, because mostly we used to not cover that part, but I started doing it. So even if it is not covered, I will cover it in the end-term revision sessions. Okay. There is just
Okay.
one type of problem that can come from there, but it's a bigger, very big problem. So we'll discuss it with time.
Hmm.
Okay, so balanced binary search trees. By now, we all know what is a binary search tree, right? The tree is divided into left subtree, right
Yes, ma'am.
subtree, and we must make sure that for every node, the left subtree is lesser than that node, right subtree is greater than that node, right? So just some basic information: how to search a key in a list of n data items. So searching, we know there are two types of searching: linear search, binary search. Linear search takes order of n time. Binary search takes order of log n time. These things we have studied in week 8 also, I hope.
Ma'am, binary search tree is based on the binary search concept.
Yes, exactly. That's why in binary search tree, the height of the tree is taken as what? Ideal tree, it is the log n height,
Yes.
right? So why this log n height happens, if you
And
want to know?
if it's not ideal, means it's a linear search.
Sorry, come again.
If it's not ideal, the worst case is
Yeah, the worst case is if you have a skewed tree. That is, the tree is like this, only in one direction.
so it's
Then
like a linear search.
this will take order of n time to search in worst case. Okay, this becomes a linear search because see, binary search means what? Whenever we get log n, that means for every decision we are making, for every node that we access, the tree is getting divided into two halves, and we only
Yes.
have to search one half, right? So with every decision, the sample space becomes half of it. That's why this searching time takes log n time. But if it is a skewed tree that all the nodes are in one side of the tree, then obviously that every decision will not make the tree into half the sample space. You have to go through all the nodes, right? So ideally, binary search tree should have order of log n height. Okay. Now these things no need to memorize any of this ordered array searching time complexity. We don't ask these things. These are more into data structures, right? No need to memorize. Just understand that a BST is balanced if height is approximately order of log n. This is what we desire. Okay. Now two types of tree we can say. One is a bad tree, that is a skewed binary search tree, that is a bad tree because it takes order of n time to search an element, or the height is order of n, right? If there are n nodes. And a good tree is when the height is order of log n. So these things, do I need to go into more details or do you understand this part?
Yes, ma'am, understood.
Okay.
Understood.
If you have any doubts, you can ask. I just want to go to the actual part from where your sums will come. Yeah. So, yeah, this part let's discuss. So, searching takes log n in a good tree, right? Optimal complexity. So, searching will take log n time inserting any element in a binary search tree. So, the insertion part is just your a fixed constant time, that is order of 1, right? And you have to obviously search the tree to find where to insert. So, that searching time will also be there. So, order of log n plus order of 1, since we don't consider constant time into the complexity part, so we just take order of log n as the entire time. Same for delete. When we want to delete a node, we first have to search the tree to find the node where it is present. That will take log n time. Then deletion is just a constant time process, so order of 1. The total complexity for search, insert, delete, all three in case of binary search tree, in a good binary search tree, is always order of log n. Okay. Assuming that it's a balanced tree. Now, okay, yeah. This is also just some theoretical information. You can just go through these slides once for your theoretical question. So from week 9, there will be one theory question, okay, in the end term. So all leaves are obviously at the same level. We know this. Height of all leaf nodes has to be same. Complexity of insert, search, delete, we just saw is order of log n. Data is kept in sorted order. Every node, leaf or internal,
Ma'am, this information, height of all leaf node are on
hmm,
same level, is for balanced search tree.
yeah, we are talking about balanced tree only. Okay, that's why we are taking height as log n. If it is not a balanced tree, height won't be log n. Okay, in a
Okay.
perfectly balanced tree, the leaves will be at the same depth. Now, all the data will be sorted. Now, this is where we come into the concept of 2, 3, 4 trees. Okay, so 2, 3, 4 trees are just a precursor before you learn about what are B trees and B plus trees. Okay, if you understand 2, 3, 4 tree, then the extrapolation from there is pretty easy. So every node, leaf or internal, in a binary search tree is a two node. Okay, no, they are not talking about binary search tree anymore. Okay, we have moved on to 2, 3, 4 trees. So in 2, 3, 4 trees, what happens? Every node is a 2 node or a 3 node or a 4 node based on the number of links or children. Okay, I'll explain this. See. So these are called 2, 3, 4 trees. not very popular. Okay, we are not actually going to use it. This is just to understand how B tree B plus tree works. So till now we have only dealt with trees where one node contains only one information, right? One key value. Now we have to get used to the idea that one node might contain multiple key values. Okay. So there are three types of nodes in a 2 3 4 tree. One is a two node. So uh, this is a two node. Now the name can be a little confusing because you can see there is only one search key value which is S, but the name is given based on how many children it has. Okay, how many child pointers it has. So a two node, that is this, has two child pointers. So the left hand side child pointer will contain search keys that are less than S, and right hand side child pointer will contain search keys that are greater than S. So that basic binary search tree property is maintained. Okay, this is a two node. Now this is a three node. Why three node? Because there are three child pointers I can see. So S and L are two search key values. Now remember, inside a node also the keys are in sorted order. So S is less than L. Fine. The greater one is stored on the right hand side. So everything that is stored in this child pointer to the left of S is going to be search keys that are lesser than S. Everything that is stored in this child pointer right of L will store search keys that are greater than L, and everything between S and L in this child pointer will store the search key values which are which are greater than S but less than L. Okay. Left hand side of S is less than S, right hand side of L is greater than L, middle one is greater than S, less than L. Okay, because it is in the right hand side of S but left hand side of L. Now we have one more type of node which is called four node. So you can understand now that four node means there are four child pointers and three search key values.
Ma'am, in such organization,
Hmm.
if there are multiple search keys with the same value,
No,
how are they
everything
stored?
will be unique.
Okay.
Okay,
Like in
unique
the
things. That's why I am using this to understand indices. See, whenever we have index table stored in the form of a B tree or a B plus tree, okay, what did we see? That search keys are usually unique, right? If you don't have in unique search keys, there is no way you can search.
no, there was one secondary index done on salary where
Yeah,
80,000
second
was pointing
index is
to
fine. Yes, yes.
uh,
But you can see that the mediator part, that is the bucket, that
okay.
is unique. Okay. For a particular search key value. Okay, this let me go back once. This, right? So here in the index table, everything is unique in the index table. That I can say.
Yes, ma'am.
Okay. Where are the duplicacies coming? In the mediator part, the buckets. So this 80,000 bucket, it has two possible values. There is two possible records have 80,000. So that is stored here in the bucket, not in the index. Index values are always unique. Okay. And we are storing just the index. So B tree or B plus trees are going to be used to store just the index table. So there are not going to be duplicates. See,
Okay.
duplicates are going to be in the tree. I'm not saying there won't be duplicate values in the tree. It's a little difficult to understand at this point. Now, okay, let me put it this way. In B tree and B plus tree, the structural differences are there. Okay. In B tree, every value is unique. Every node has keys which are unique. But in B plus trees, some duplicacies are there, but those are not duplicate values. The same values are repeated on some levels. Okay. So the actual search keys are unique, but since the structural differences are there, so some duplications are there in B plus trees which are not there in B trees. But those are not duplicate search key values. The same search key value is repeated in certain levels uh, because of accessing issues. Okay, we'll discuss that when we go to B tree.
Okay, ma'am.
But usually everything will be unique. Okay. So four node also same thing. You can see four node means, see this, if I call it an n node. Okay, that means how many child pointers? See, two node,
N
two
plus 1.
child pointers.
N
No.
plus 1.
If I have a
And
two node, I have two child pointers. If I have a three node,
and
I have three
Oh,
child pointers.
okay, ma'am.
So n node
and
means,
are you referring to the arity of the tree?
yes. order. Okay.
It's arith
So we
yeah,
are referring to the order of the tree. Look,
like
I
it's
don't want to use this term right now because order we will come to when we go to B tree. One second. Just give me a second. Yeah. Okay. So in an n node, how many child pointers will I have? N. How many key values will I have?
N minus 1.
N minus 1. Okay. So this is what we call an order of a tree. Okay. So n will be the order of the tree. Later on, we'll discuss this. For now, you just have to understand we are studying something called a 2-3-4 tree, which contains three types of node. One is a 2 node, 3 node, 4 node, three types of nodes. But the name of the nodes is not based on the key values, it is based on the child pointers. So if I have an n node, it means the node has n number of child pointers. Okay, and n minus 1 number of keys it can hold. Now, there is something called a node split. Okay, so since 4 node is the maximum, right? This is the maximum order node that I have in this tree. That is, a 4 node is the biggest node I can have. Now, what if another element comes which I need to insert in a 4 node? So that's not possible because we have already reached the limit. So then we split that 4 node, okay, to make it a smaller node, maybe a 2 node or a 3 node like this. So if it is, first of all, see, insertion is very easy. You have to search to find the expected location. If it is a 2 node, you can insert it. See, if it is a 2 node, it will look like this, right? Some key value here. If I want to insert one more key value here, then the node becomes something like this: k1, k2, and 3 child pointers. So this is a 3 node. So in a 2 node, if you enter another key value, it becomes a 3 node. In a 3 node, if you enter another key value, it becomes a 4 node. But if it is already a 4 node and you want to insert one more key value, then it is not possible. So then we have to split that node by moving the middle term to its parent node. Okay, inside of discussing all this theoretically, let's take an example. See, this is one type of splitting. Okay, splitting at root.
Ma'am,
So, yeah.
here on the left hand side, when you're saying A, B, C, and D, is that what you're terming as node or the?
No, node is this. Okay, and these are key values. S, M, L are key values. A, B, C, D are child pointers.
So we are talking about the ones on top or
We are talking
SML?
about the keys. SML.
Okay, SML is the keys,
Yes.
and this is considered as one node or three
This
node?
whole thing is one node.
One
Okay.
node.
This is called a 4 node because it has 4 child
Four
pointers, 3
children.
key values.
Thank you, ma'am.
Okay. So what happens? See, two types of split can happen. Okay. Either I can wait for a value to be, want to insert. If a value comes and I need to insert it into a 4 node, then I wait to split the 4 node at that time. Otherwise, we can do one more thing, that whenever we encounter a 4 node, we will split it beforehand. Okay. That way the insertion becomes easier. Even if a 4 node is there and it doesn't need any more values to be inserted in it, we can still split it beforehand because we know that at some point it will need to be splitted. Okay, so that these are two strategies. One is the early split strategy, one is the later one. So that also we'll discuss. First, see what is splitting. This is a 4 node. Now if I want to split this 4 node, what happens? The middle element, that is M, remember, everything is sorted. S is the smallest one, M is the middle element, L is the largest one. Okay. So left to right, it is sorted in increasing order. So to split this node, you have to take the middle element and take it one level higher. Okay. So M will go one level higher and S and L will become its child nodes. So M is now a what kind of a node? Is it a 2 node or 3 node or 4 node? Just
Two node.
M.
Two
It's a
node.
2 node.
It's a 2 node. Similarly, these are also 2 nodes now, S and L. So 4 node can be split into 2 nodes like this. Okay. Now see, splitting with 2 node parent. So let's say P is a 2 node. It has a left child pointer, a right child pointer. The left child pointer points to a node which is a 4 node. Okay. So in this case, if I want to split this 4 node, how will it work? So I'll take the middle element M, take it one level higher. So one level higher is this parent node P. So M will go into the P node. Okay, in the same node as P. Now, since M is present on the left hand side of P, then what can we say for sure? M is less than P. Right? This property is clear. So M will be inserted to the left of P. Okay, first M, then P. Now see. S was what? Is S less than M or greater than M?
Less than M.
So S will become the left child of M. Okay, so this became the left child of M. L is what? L is greater than M, but less than P.
Yes.
So it becomes the middle child. And we don't have anything that is greater than both M and P, right? Except for this E, which was already present. So there is only E present here. Similarly, if the node was on the right hand side, this 4 node was on the right hand side of P. So now what do we know? S, M, L. All three are greater than P. This is clear. Again, among these three, S, M, and L, S is the least one, M is the middle one, L is the largest one. Right? So if I now want to split and take one level higher, M will go one level higher. M will be stored to the left of P or the right of P?
Left of P.
M I'm saying. M is greater than P, right?
Right of the tree.
Right.
Right of
Right
P
of
because
P.
it's sorted. So P is the smaller one, so that comes to the left. M is the larger one, goes to the right. Now S, talk about S here. S is less than M, but greater than P. Right? So it will be the middle child. L is what? L is greater than M as well as greater than P. So L can be the right child of M. This is how splitting works. Okay, this is very basic splitting. Now, if you have a 3 node parent like this, so PQ is a 3 node, right? And this is a 4 node. So splitting only occurs when we encounter a 4 node. Otherwise, in a 3 node also you can insert an element without splitting it. 2 node also you can insert elements, but 4 node is already filled. Nothing more can be inserted. So if this is the type of tree you're dealing with, then if you need to split this 4 node, so M will go one level higher. So here what can we say about M? M is definitely less than P, right? If it is less than P, it is obviously less than Q, since Q is greater than P. So M is less than both P and Q. So M will go to the extreme left here. S is what? S is less than M and also less than P. So S will go to the extreme left, left child of M. L is greater than M but less than P. So it becomes the middle child. Similarly, these two. Okay. Here also see M is, so from this picture, what can you say about SML with respect to P and Q?
They are greater than P and lesser than Q.
Right. So that's why they're the middle child. Right. Now, if I want to split it, M will go one level higher. Where will M be stored? In the middle. It is greater than P, less than Q. So M comes in the middle. S is less than M, but greater than P. So this child between M and P. L is also greater than M, but less than Q. So L becomes the right hand child. And if it is in the extreme left, then we can say all three SML are greater than P and Q both. So if here I want to make the split, M will again go one level higher, but it will be stored in the extreme right because it is the greatest value among P, Q, and M. So M is the largest value, comes to the right. S is less than M but greater than Q. So it is the middle child of Q and M. L is greater than M and greater than PQ both. So it is the right hand child of M. These three things clear?
Yes, ma'am.
Now two types of splitting strategy we have. One is early split, one is late split. So in early split strategy, what we do is we split a 4 node as soon as we cross on in traversal. That means if I am traversing the tree and I encounter a 4 node, I will immediately split it. I won't wait for some other key to be inserted into it. I will immediately split it as soon as I see a 4 node. Okay. What does it ensure? That the tree does not have a path with multiple 4 nodes. See, what happens if I have multiple 4 nodes in a row? Okay. Let's say I have a node like this, which contains A, B, C, and these are all the children. Now, this left child of A contains another 4 node, which is D, E, F. Now, say I want to insert G in this node. So there will be a split. Which of these elements will go one level above?
E.
E will go one level above. Where should E be stored?
Left of A.
Left of A. So that means here E should be stored. But this is also a 4 node. So in order for this to be stored here, this node also needs to be split.
B should go
So
up.
there are multiple splits in the way. So this increases the time for insertion. Okay, that's why early split strategy is advised, so that there are not multiple 4 nodes are present in a single path. Okay. So that is early split. Late split is nothing but the opposite. That is, you only split a 4 node when you need to insert an item in it. Otherwise, you let it be. Okay. But in this case, there can be, for one insert, you might need to perform multiple splits. And in the worst case scenario possible, it can be, the number of splits can be order of h. That means whatever is the height. So the entire path contains only 4 nodes. This can also happen if you don't follow early split. Okay, both are valid, but we are going to be following the early split strategy. So whenever we see a 4 node, whether we need to insert something in it or not, we will split it immediately. Okay, this is an example of how to create a 2 3 4 tree. Okay, so these are the key values that we are going to insert in this exact order. So first key is 10. So this is the first step of insertion. What type of a node is this?
2 node.
2 node. Okay. Then I enter 30. 30 is greater than 10, so it comes to the right hand side. Now it becomes a 3 node. This is the second step. Third, you have to enter 60. 60 is greater than both. So first you do the comparison inside the node. 60 is greater than both 10 and 30, so it goes to the extreme right. Now this becomes a 4 node. What strategy are we following? Early split. So as soon as a 4 node is found, we are going to split it. So which of these three should go one level above? 30. So 30 now becomes the root node. Okay, and the child are 10 and 60. 10 is less than 30, so left child. 60 is greater, so right child. This is step 4. Okay, next, what is the item? 20. So in this tree, first you search from the root. 20 is less than 30, so goes to the left child. 20 is greater than 10, so I can insert 20 here. Will it be inserted to the left or right?
Right.
Right.
Right of 10. Okay, so it looks like this. Fifth step. 20 is inserted. Next, I have to insert 50. Again, start from the root. 50 is greater than 30, so go to the right child. 50 is less than 60. So I can insert it here to the left of 60. So it looks like this. This is the sixth step. Next, I have to insert 70. Okay. No, sorry. Next, I have to insert 40. So this is the seventh step. So 40, where can I insert 40? In this tree, if you check, 40 is greater than 30, so right child. Here in this node, 40 is less than both 50 and 60. So it should come as the extreme left element. As soon as we enter 40 in the left element, this becomes a 4 node. So we have to split it, since this is early split. So if I split it, which one will go one level higher?
50.
50. So 50 comes to the root node now. 50 is greater than 30, so it is stored on the right hand side. Now, what about the other two elements in this node? 40. 40 you can see is less than 50 but greater than 30. So it is the middle child. This one. 60 is greater than both, so it becomes right child of 50. Okay. Next, I have to enter 70. So again, search from the root. 70 is greater than 30, greater than 50, both. That means it will be the right child of 50. In the right child of 50, there is 60 present. 70 is greater than that also, so it will come to the right of 60. So it becomes like this. Okay, this is a 3 node now. Now I have to enter 80. 80 is also going to come in this right hand side of the tree, and it is greater than both 60 70, so we can enter it at the extreme right, but again this forms a 4 node. So now which one will be taken one level higher?
70.
Now 70, if I take it one level higher, it comes to this node and it will be stored like 30 comma 50 comma 70, but this is also turning into a 4 node. This is also now a 4 node. Okay,
So we have to split it also then.
we have to split this also. So in this slide, the immediate splitting is not shown for this node. See, they have entered the other elements first. They have entered 80. So 80 will now again come in this node. This again becomes a 4 node. They have entered 15. So 15 also, when we enter it in this node, it becomes a 4 node. So now we have all of these 4 nodes. So we have to split every one of them. Okay. Now, see, this is a representation of late split. Okay, that we are leaving these. We are not splitting immediately. We are waiting for some other element to try to enter one of these four nodes. So when I have 90, in this tree, if I want to enter 90, so start from the root. It is greater than all three elements in the root, so it will go to the right hand side. Okay. Wait, okay, this one they have, I think, already split with 90. 10, 15, 20, 30, 50, 70, 40, 60, 80. No, 90 split hasn't occurred yet. So first I can enter 90 here. Okay. Next, if I have to enter 100, 100 is also greater than all of them. So 100 should come here. Now this becomes a 4 node. Okay. So if you keep them and not split, then it becomes a late split. That is, if you have some other element trying to enter a 4 node and then only you split it, then it becomes a late split. But if you split the nodes, the 4 nodes, before an element is trying to enter the 4 node, then it's an early split. Now see, how many 4 nodes do we have in this tree?
3.
3 4 nodes we have. But is any other element trying to enter any of these 4 nodes?
No.
So that means this is still in early split. Okay, still in early split. If we split it now, it will still be early split strategy. So now we will start splitting with this node. Okay.
So ma'am, we kept entering the
we kept
element,
making the 4 nodes. Yes.
4 nodes. Yeah. Okay. We did
Okay.
not split till now. We
No,
can
we
say.
did not split till now, but it is still early split because no other element is trying to enter the 4 nodes.
Understood.
Okay. So if I
So
start splitting,
we should concern about splitting only if something we are
is
entering,
yeah,
trying to enter all.
if you are having a late split strategy, okay, then if something is trying to enter this 4 node, then you split. In early split, you can, and if you split the 4 node in time before something else tries to enter it, then it's early split.
But this is still, we have exhausted our elements filling, na ma'am?
Yeah, we have
Now,
exhausted it, but
so we
nothing
have
else is
created
trying to enter it.
correct, but we have created a tree without any split, and now just for the sake of splitting, we are splitting it.
Yeah, just because we have
show.
early split strategy, that's why. If you keep the tree like this also, then also it's fine. Okay, but since we have early split strategy, that's why we'll split these nodes.
Yeah. So if we have this tree like the left hand side tree, and then probably after 90, if some element is there.
Yeah, 100 is trying to enter, so I can enter it here. This also becomes a 4 node.
And we'll keep it like
Yeah.
that. If we are
Now,
following the late strategy.
Yeah, if you're following late strategy, we'll keep it like that until something else, maybe 101 tries to enter this node. Okay, but early split, so we'll split this node. So how it is splitting, see. First we have 80, 90, 100 here. Okay, 10, 15, 20 here. We have already split this node. 30, 50, 70. So if I split this node, 50 should go one level up, right? So 50 is now the root node. 30 is its child, left child, 70 is its right child. Similarly, based on that sorting, every other node is assigned as some left or right child. Like here, see, 10, 15, 20. This node was on the left hand side of 30. That means all of these are less than 30, right? So these should be in the left child of 30. 40 is greater than 30 but less than 50, right? So it is right child of 30. Similarly for 60 and this node. Now these two nodes also need to be splitted, right? But that is not shown any further. If we split this, what will happen? 15 will take
Before
one
30
level up.
left.
Yeah, it will go to here, and here 90 will go one level up, 70 comma 90. Okay, no more splitting is required. Just you have to rearrange the leaf nodes.
There's a mosquito here near my leg.
Okay.
Yeah,
Ma'am,
So this 2, 3, 4 tree is clear for everyone.
What?
yeah, it's off. Ma'am,
Any doubts? Anyone?
This
if
way?
hello, ma'am.
Okay. Yeah.
If after 100 there would be one more element, 7. It would have entered into
7.
left to 10, right?
Yeah, it would be trying to enter here, but not possible. So first we have to split this node.
So, ma'am, it is late strategy. Now, why early? Like,
Yeah, if there was an element, then it would have been late. But since there is no such element, it is still in early strategy.
okay.
Okay. Now see, 2, 3, 4 trees will actually not be in any of your questions or anything. It is just to make you understand the concept of how one node can contain multiple keys. Okay. So this theoretical parts, please just go on your own. This is not difficult. The same things we have discussed is written here. What
So
and do not take these things, okay? Do not, please don't work with these values that are given here. I will give you a formula sheet because much ambiguity is there, okay? So different books have different values for leaf node, how many children it might have, all these. So I have a sheet where we have the formulas that we use. I'll give that to you. Okay, just memorize those formula.
ma'am, one question. You were saying that 2, 3, 4 nodes will not come in the exam.
Exactly, this 2, 3, 4 tree will not come. Okay, we will ask questions from B tree, B plus tree, which is a generalization of this 2, 3, 4 tree.
Okay, ma'am. Thank you.
Okay, yeah. So 2, 3, 4 tree, what happens? See, there are 3 types of nodes in this tree. In B tree, B plus tree, there are only one type. Okay, so that is defined by the order of the node, order of the tree. So if the tree has order n, then every node has an order of n. Okay, that means every node can have n number of children and n minus 1 number of keys in them. That is the basic structure of B tree, B plus tree. Okay, now obviously there are structural differences that we will discuss. Yeah, what I was saying is when you go through this theory part of the sheets, just for now, don't remember these exact formulas, okay? I will give you the sheet, please study from there because some ambiguity happened in the previous terms, so I'm not advising to study this ones. This is
Ma'am,
still
only
okay. I
these
mean,
2 slides or the entire deck?
no, okay. See, for 2, 3, 4 trees, this is still okay. I mean, you can study from here. But when we go to B tree, B plus tree, then there will be actual questions on how many nodes can be present in a half-filled node, how many key values in a half-filled node, how many children every leaf, every internal node can have. So there are particular formula for that. B tree, B plus tree, I will give you the formula sheet. Okay.
Okay, ma'am. Thank you.
So see, one thing I will say, how much time we have? Half an hour. Okay. B tree, B plus tree is a concept that should be studied together. If I start it today, I won't be able to finish. So I will advise you do this in the next class. Let us complete hashing today. Is that okay? Or do you want to continue with this? Whatever you choose. Because I am not sure if dynamic hashing will be discussed in next class. That's why.
Ma'am, then hashing you can discuss now.
Is everyone okay with that?
Yes, ma'am.
Okay. See, 2, 3, 4 trees is the basic concept. If you understand that, B tree, B plus tree will be very easy. It's just formula related. Okay. Only sums will come from here. So I will give you this PDF after the class. You can go through these. So I have just taken the same PDFs from your slides, but I have taken only the important ones. Okay. So B tree, B plus tree, I will ask the instructor to take it in the next session. Let's start with hashing. So static hashing, okay, it's the first concept. 2 types of hashing, static and dynamic. So just by the name, you can understand that what can be the difference between the two. So in static hashing, we have some fixed storage, right? Dynamic hashing, the storage can dynamically change according to our requirements. So which one do you think is better?
Dynamic.
Dynamic, right? Static hashing has more collisions. So let's understand what is that. See, one more thing, if you go to the YouTube channel, in the videos that we have uploaded, I have uploaded one video just understanding what is static hashing. Okay, so please go through that video once. I have discussed examples and the theory part also. So,
Ma'am, how do we identify that video which you have uploaded?
Okay, let
Any
me show you
particular
quickly.
name?
Let me quickly show you once. It is called static hashing only. Right. I'll upload one more for dynamic hashing too. So, okay, this is visible to you. Can you see the YouTube channel?
Yes, ma'am.
Just go to the videos part. Okay, here, this tutorial on static hashing, this one.
Thank you, ma'am.
Okay, just check this out. I'll upload one on dynamic hashing too. If someone misses the class, they can study from there also. Okay, now let's understand. So hashing involves something called a hash function. Okay, this is just one more way of implementing your indexing. So the indexing that we studied at first, right, that faculty table, how you can form an index. So index can be implemented in two different ways. One is this hashing method, one is the B tree B plus tree method. Okay, so static hashing is what? A hash function H maps data of arbitrary size from domain D to fixed size values. So easier way to understand this is, let's say I have that same, okay, the search key concept prevails here also. So I want to make an index, a hash index based on search key values. Let's say I have 100 search key values. Okay, those are names of people. So that's the domain of my data D. Okay, now I need to map this to some fixed sized values. Let's say I have, in hashing, something we have is called bucket. Okay, so hash bucket. So these 100 search key values can be mapped to 10 buckets, let's say, for example. So that's why hashing is a very efficient procedure. Okay, how this mapping is done is that is based on the hash function. Okay, so every bucket has some hash value associated with it. So what we will do is, we have the keys, okay, and we have the hash function given to us. So we will apply the hash function on each one of the keys, and that will generate a hash value, which will tell us correspondingly to which bucket I can assign this search key. Okay, it can be a little tough to understand in the beginning. See, let's say I have search key values that are 100 search key values I have. Let's say they are all numeric values. Fine. And I have 10 hash buckets. Each hash bucket has a hash value associated with it, 1, 2, 3, 4, like this. And I have some hash function, let's say n mod 10. Okay, this is the hash function. N is your search key. So for every 100 search key, you put it through that hash function. Whatever value it generates, you store this search key in that corresponding bucket having that same hash value.
Ma'am,
Whenever,
sorry, ma'am, are you displaying some other?
No. I'm just talking. Okay, I'll write it later on.
Okay.
So for a given key k, for any search key k, and a hash function h of k is called the hash value. That is, after applying that function on that search key, whatever value is generated is the hash value or the hash code.
It's a real number.
It's a number, yes. So that hash value will be associated with some bucket.
Many keys can have the same hash value?
Yes, that's the thing I was going to say next. So every bucket has some storage capacity. Okay, maybe let's say each of your buckets can store 2 records or 2 search key values. But what you need to make sure is that every bucket has the same size. If one bucket can store 2 records, every bucket should store 2 records. Okay, now this hash value will assign the bucket number for a particular search key. Now let's say there are 2 search keys k1 and k2. Okay, and h of k1 and h of k2 both are giving the same hash bucket value. Now, just for example, if that bucket has only storage to store one search key, that is also possible. So in that case, what happens is a collision. That is, both of these search keys are trying to enter into the same bucket, but the bucket only has space for one. So that is a collision. Okay. Hash function should be collision free and fast. So this is not, see, ideally what we want is a random hash function. Okay. Random hash function is ideal. Why? Because what we want in a desired hashing technique is if we have 10 buckets, okay, each of which, for example, let's say stores 2 records, okay, then we want the hash distribution to be such that every bucket is first half filled. That means first if I take 10 hash values, okay, if I take 10 search keys, generate the hash values and assign them to buckets, in an ideal hash function, every bucket should have had one search key stored in it. It is that uniform distribution that we want. Okay, not that all 10 search keys are trying to enter into the same bucket. That's a bad hash function. So a hash function should be uniform. Okay, desirably uniform. Now, when do we get such uniformity? When we take random hash functions, right? Even then also you cannot guarantee. Okay, so no hash function is ideal. Just we try to get a more uniform distribution. That's it. That is, if we have 10 buckets where each bucket can store 2 records, ideally the search keys should be evenly distributed among the buckets, not that all the search keys are trying to enter into the same bucket. Do you understand the in uniform distribution part? Okay. See. For example, take this. So what are the keys? John Smith, Lisa Smith, Sam Doe, Sandra Doe. Okay. Now some hash function is here. We don't know what it is. But after passing the search keys through that hash function, we can see that John Smith and Sandra D, they both are assigned to hash bucket with hash value number 2. Lisa Smith is assigned to this bucket 01. Sam Doe is assigned to this bucket. But since John Smith and Sandra D are both assigned to this bucket and it has only space to store one record, so this is a collision. So we now don't know which record to enter here. So ideally, hash function should not do that. A bucket is nothing but a unit of storage. Okay, it can contain one or more records, but the bucket size should be fixed for every bucket in the hash table. Okay, in hash file organization, we obtain the bucket of a record directly from its search key by using the hash function. Like I said, for every search key, we will first put that search key through the hash function. That will generate some hash values, which we will take to understand that, okay, to this bucket I can assign this record. Every bucket is also associated with a hash value. Okay, so hash function is used to locate the records for access. That means with a hash function I can assign a particular search key to a particular bucket. Okay, now records with different search keys can also be mapped to the same bucket. That totally depends on the hash function. See, in an ideal world, if we had an ideal hash function, the entire distribution would be uniform. That means if I have 20 records, if I have 10 records, okay, if I have 10 records, 10 search key values that I need to store in the buckets, and there are 10 buckets where each bucket can store only one record, then ideal hash function would make sure that each one of the search key values are assigned to a particular bucket, right? And if it is a bad hash function, then all the search key values will point to the same bucket. So there will be a lot of collision. So we try to find such hash functions which are random, which guarantee a uniform distribution or as close to it as we can get, and which guarantees that there will be very less collision and it will be fast. Okay. So all these things I have discussed in much more detail in that tutorial video. So please check that out once. Okay, I hope now you have an idea. Now we'll start to see how it works. Okay. So let's say I have an instructor file and I'm using department name as my search key. So there are 10 buckets. Okay. Now binary representation of ith character is assumed to, okay, this is just too complicated. Let's take a easier example. This is binary representation. So the ith character is assumed to be integer I and hash function returns the sum of binary representations of the characters modulo 10. Okay, so just for example, let's think of it as I had one more example. Where is that? Yeah, let's do this. This one is much easier to understand. No need to go into all that binary and everything right now. So here you can see this instructor table is given. Let me increase the size. You can read the values, right? In the buckets, are the values visible?
Yes, ma'am.
Okay. Now think of it like this. This is the instructor table. I want to create the hash table or the buckets based on the ID attribute. Okay. So how many buckets do I have here?
8.
8 buckets.
Oh, 8, ma'am.
8 buckets. See, bucket 0 to bucket 7. That means total 8 buckets.
Yes, yes. Okay.
Okay. So if I have 0 to 7, that means total of 8 buckets I have. Now what is the hash function? Hash index on instructor on attribute ID. That means ID is my search key. How is it computed? It is computed by adding the digits, then taking a mod 8 of it. Okay. So let's take the first ID, which is this one, 76766. So according to the hash function, let's call this key K1. So the hash function is saying it is a sum of digits modulo 8. So h of K1 should be what? 7 plus 6 plus 7 plus 6 plus 6. Whatever this value is, we'll take a modulo 8 of that. So what is this value? 18 plus 14 is 32.
32.
32 mod 8 is
0.
0. That means this is the hash value. So what is the corresponding bucket? Bucket 0. Bucket 0 is storing this search key. Now, see, similarly, bucket 1, bucket 2, all of these are filled like this. Now, bucket 5, see, 15151 mod 8.
What's the capacity of bucket? We have decided 2.
Yeah, 2 is the max capacity of every bucket.
Okay.
So every bucket can store 2 search key values. So 15151, what is the sum of digits? 13. 13 mod 8 is 5. So it is stored in bucket 5. Similarly for 3, 3, 4, 5, 6 also, it shows bucket 5. Now this bucket is completely filled, right? But when we come to this value, 58583, what is the sum of this? 13, 16?
29.
29. 29 mod 8 is 5 again.
5.
But now when I try to enter this in bucket 5, no more space is left. So this is again a collision, right? How do I deal with such collision? One method is called chaining. Okay. Whenever a bucket is fully filled, but still there are more search key values which are trying to be assigned to that particular bucket only, then it's called an overflow. Okay. So whenever this third entry tried to enter in this bucket, this caused something called an overflow. This becomes an overflow bucket. Okay. So to handle this, we are going to use something called chaining. Okay. That is this arrow that you are seeing. This forms a chain-like network. So we have one, now we add one more bucket with the same hash value, which is linked to this bucket 5. Okay. How this is implemented is using a linked list. Okay. So bucket 5, this bucket is just an extension of bucket 5. So whatever value is trying to enter here will now be entered in this bucket. Okay, overflow chaining is just one method to handle collision. Similarly, when 98345 this value comes, this also tries to enter in bucket 5. It sees that, okay, this is filled, so I'll go to the next chained bucket, which is this one. Okay, like this, if there are more search key values which are trying to enter in this bucket, so once the second bucket is filled, you again chain one more bucket to it. Okay, like this, the chain will continue, but this is a bad thing. Okay, for the time complexity, this becomes bad. Because now when you try to search the buckets for the hash values, for the search key values, see, if I want to search 98345, first I have to search the buckets. So somehow I reach bucket 5, that okay, the hash value is generated as 5, so bucket 5 I will search. In bucket 5 I cannot find it, so I have to go through the chaining to the next bucket. Again do a linear search. So here the complexity increases. Okay, that's why chaining is not a good practice, but it is implemented anyways. Now, why is this happening? This is because we have the bucket size fixed, right? That's why this is called static hashing. Because once the bucket size is fixed, we cannot change it. Every bucket will have only two search keys. So to solve, this is one of the reasons why we have dynamic hashing. Okay, to help with the time complexity. Is this example clear for everyone? How the hash values are assigned?
Yes, ma'am.
Yes, ma'am.
So what are the deficiencies of static hashing? See, you will get sums like this in your exam. Okay, so hash values, search key values will be given to you. Hash function will be given to you. Okay, and we will ask you that which one question type is this, that okay, the let's say 5 or 6 search key values are given. Okay, and 2 or 3 or 4 hash functions are given, separate hash functions. Now the question is asking which of these hash functions will generate unique hash values. So that's the best, right? If we have unique hash values, that means collision is not there. Each of them are assigned to a unique bucket. So you have to apply that hash function, all 2, 3, 4, how many hash functions are given in the statement. You have to apply all the search keys to each of the hash functions and find out which one gives unique values. So that type of problem takes a little more time, but still there are good marks associated with it. Okay, that is one type of problem. So this type of problem also I've discussed in that tutorial. Okay, we'll take it up here also. But first, what are the deficiencies that we saw? In static hashing, function h maps search key values to a fixed set of buckets b. Right, the number of buckets is also same and the size is also fixed. Now, size is fine, but number of buckets making it fixed is not a good thing. Because, see, two things we can do. One thing we know is that databases are dynamic structures. They grow or shrink with time, right? We either insert things, delete things, update things. It is not a static structure. So initially, if we take a large number of buckets to avoid collision, that okay, I will take such a hash function which generates over a large number of range of hash values. So huge number of buckets I have. But initially, let's say my database only has 10 rows. But in static hashing, since your number of buckets is fixed, all that memory is already allocated. Okay. So even if your database doesn't require all that space, it is getting wasted since you already allocated it. Also, if you have too few number of buckets, you decide to save some storage and allocate only a few buckets initially. But later on, your database grows in number of rows. Okay. So now you have a lot more search keys. But the bucket number is fixed, so there will be too many collisions. So none of these things can work. Right? One thing will waste space, one thing will lead to too much collision. So one solution is that periodic reorganization of the file with a new hash function. What does this mean? Even though the database is dynamic, that means it is changing over time. So what we can do is maybe we can set some intervals, that is every 3 months we are going to reorganize the file and introduce a new hash function, right? So again, new number of buckets, everything is reorganized, but that's a very expensive solution. To implement this in real life will cost a lot. Every 3 months if you have to reorganize your database. Okay, 3 months is still a long time. You may need to do it even more often. So what is a better solution? That you allow the number of buckets to be modified dynamically. That whatever is my requirement, according to that, the number of buckets will change. That's the best solution, which leads us to dynamic hashing. So static hashing is clear for everyone. Any doubts? Okay, good. We'll see when we solve problems. So now dynamic hashing. Okay, now this one will take some time. I'll explain this with the help of an example. Okay, don't go into all the theory, just understand the example. That will be better. So first thing is that it is also known as extendable hashing. Okay, why extendable? Because see, here the hash function, usually in static hashing, the hash function generates values over a smaller range, like we saw mod 8. If we have a hash function that applies mod 8, what is the range of values that the hash values can be? What is the range?
0 to 7. 0 to 7. So very small number. In case of dynamic hashing, we make sure that the range is much greater. Okay. That means we can generate as many number of buckets as we want. So what do we do? Okay, you know this. If I have 3 bits, how many combinations can I form? 8. Right? 2 power 3. So 8 combinations. So if I have n bits, I can have 2 power n combinations. Now 2 power n combinations means what? If we translate it into this hashing language, it means in extendable hashing or dynamic hashing, we use b bit integers. Okay, b bit integers, where b is usually 32. Okay, or something just as large. So if I have 32 bits, that means how many combinations are possible? 2 power 32, which is a big number. So that many number of buckets are possible. Understand? This b bits means what? This is the number of bits which we use to represent buckets. So if I have 32 bits to represent a bucket, so how many buckets can I represent in total with 32 bits? 2 power 32 buckets. Is this clear? See, if I have a
Yes.
4-bit representation, okay, that I have all these hash buckets. Each hash buckets is represented using a 4-bit value. So how many such hash buckets can be there for unique representation? 2 power 4.
2 power 4.
So 16 such buckets I can have. Each of them I can identify uniquely using 4 bits. So here in extendable hashing, we use 32-bit values. That means 2 power 32. That's a huge number. That many buckets I can use. But I am not assigning them immediately. Okay, I'm not assigning 2 power 32 number of buckets. I will use them as needed. Okay, but I have that range in my hand. So see, what happens here is that at any time we just use a prefix of this 32-bit value. Okay, I'll just go to the example, otherwise this part won't make sense. Don't worry about all this right now. Okay, see this. So here I am trying to form a dynamic hashing structure for a table, let's say that faculty table. Okay, where the search key I am using is the department name from which each faculty belongs. Now for each of these department names or each of these search keys, I have assigned a 32-bit value, which is the hash value. Okay, so some hash function I have generated, in which if I put this department name as search key and then run that hash function, it will generate some 32-bit value. Okay, just like we were using search keys before. And so there we had some that mod 8 was a hash function and mod 8. So like that here also h is some hash function, which if I give this search key value, it will generate some 32-bit hash value. So for biology and computer science, all of them we have 32-bit values given. Okay, now how am I going to use these values to put them in the corresponding buckets? See, very carefully understand this. Okay, so this is my table. Okay, this is the actual table. Here you have the instructors and correspondingly you have the departments. Now initial hash structure, I am saying that bucket size is 2. Okay, bucket size I'm keeping fixed. Number of buckets will vary. Okay, that's the dynamic part. Number of buckets will vary, but the bucket size is 2. So something else we have is called a bucket address table. Okay, bucket address table is what? It will just identify each bucket. So the address of the bucket will be stored here. Okay, all of this will become clear. So first we have to insert the records for Mozart, Srinivasan and Wu. Okay, first for these 3 records I want to insert the search keys in the hash buckets.
Ma'am, bucket size is fixed, hence overflow is possible here also.
Possible, yes, but the chances are very less because since there are so many hash values available to us.
Okay.
So first search key that I want to assign a bucket to is the record for Mozart. So see in the table, Mozart is from which department?
Music.
Music. Now go to the hash, this table, hash values. So for music, what is the hash value? This 32-bit value. We will first start working with only the prefix. Okay, only 1-bit prefix we'll start with. So what is the first bit? We'll start with the most significant bit, that is the leftmost, this one. So first bit is 0, right? Now see, if I want to enter Mozart, I am taking 1-bit prefix first. The first bit for music is 0. Okay. So 1-bit prefix means what are the possibilities for 1 bit? If I have 1 bit, how many combinations can I have?
2.
2.
2 combinations. What are those? 0 and 1. Right? So let's call this 0. Let's call this 1. So this is the size of the prefix. Okay. This is prefix size. So we are using 1 bit currently. 2 possibilities are there. One hash value will be 0. One hash value will be 1. So 2 different buckets are possible. So let's call this bucket as 0 bucket. This is the 1 bucket. So first we have to enter Mozart. What is his bit? First bit 0. So he will go in which bucket?
The
0
top
bucket. This one. Next we have to enter Srinivasan. Again, see what is the department for Srinivasan? Computer
computer
science.
science.
What is the first bit for computer science here? 1.
1.
So he will go into the 1 bucket. Okay, not the same one as Mozart. He will go into this bucket. Next is Wu. Okay, Wu is from which department? Finance. Finance, what is the first bit? Again 1. So finance will go into which bucket? With Mozart or with Srinivasan?
Srinivas.
Srinivasan, because both of them have the same bit, right? Same prefix. So they go into this bucket. Now this bucket is filled. Okay, bucket address table works how? See, bucket address table, currently we are working with 1-bit prefix. So there are only 2 possibilities, 0 and 1. So 0 is pointing to the 0th bucket, 1 is pointing to the first bucket. This one. Okay. Now next I have to insert Einstein record. So Einstein, see here, what is his department? Okay, wait. Physics. What is the 1-bit value for physics?
1.
1. So which bucket should it go to?
Bucket. The
1.
second.
Bucket 1. But is bucket 1, does it have any more free space?
No.
Each bucket can have 2 records. This bucket is already filled. So now what I can do? Will I do chaining?
Or you'll take 2-bit prefix.
Correct. So I will just extend the prefix. That's why this is called extendable hashing. Okay. So now I will take the first 2 bits to create more combinations. So physics first 2 bits is what? 1, 0. Right? So similarly, since now you are taking 2 bits, so the hash prefix has to be changed here in the bucket address table. Now the prefix becomes 2. So we are taking 2 bits. That means how many combinations possible?
4.
What are those?
1 0 0 0 1 1 1.
0 0 0 1 1 0 1 1. Correct. So now it will look like this. See, 2-bit prefix 0 0 0 1 1 0 1 1. Okay. Mozart was starting with what? 0.
1 bit.
So we will call this bucket. Now everything is addressed as 2 bits. Okay. Once you extend the prefix for any of the buckets, all the buckets have to be addressed in the similar manner. Okay.
Oh.
Even though in see. Okay, let me try explaining it in a different way. So which bucket did I find the collision in? Bucket 1 or bucket 0?
Bucket 1.
Bucket 1. So that's why I extended the prefix. So bucket 1 prefix will be extended right now along with this. Okay. So see in this hash address, in this address table. Okay. Which one of these 4 combinations start with 0 as prefix? How many combinations start with 0?
The first 2.
First 2. So first 2 will point to the 0th bucket because this is still using 1-bit prefix. Okay. This bucket is empty, still has 1 empty space, still using 1-bit prefix, no need to extend it. But since the collision was found in bucket 1, so here again I have to extend the prefix. So extend prefix for both finance and computer science. See, Initially, bucket 1 had finance and computer science, right? So what are the 2-bit prefixes? See, for physics, 2-bit prefix is 10. Computer science, what is the 2-bit prefix? 11. Finance, what is 2-bit prefix? Again 10.
10.
So which of these match?
Physics and finance.
So physics and finance will go into the same bucket. Computer science will go in a separate bucket. See, in the 10 bucket, we have finance and physics. And in the 11 bucket, we have computer science. Up to this, is it clear?
So these are made into separate buckets, but 0001 is in the same bucket.
Yeah, because till now we didn't need to use 2-bit prefix for any, prefix that starts with 0. Since we only had one entry, so 1-bit prefix is enough for now. Okay, so we are saying that both of these can go into this first bucket. But in the second, when we got the collision, so whatever values are present in the collision bucket, for them also you have to extend the bit. Okay, to find the correct ones, that which ones match, they should go in the same bucket. So since finance and physics matched in their hash values, so they will go in the same bucket, that is the 10 bucket. Srinivasan from computer science, the hash value was 11 prefix. So it will go into the 11 bucket. For now, these two are in the 0 bucket. Okay. We will extend these into 2 different buckets when necessary. If we find 2 records, okay, which have 00 prefix, so they will go into the 00 bucket. If I find 2 records which are having 01 prefix, they will go into the 01 bucket. But till now we haven't found, so we are not extending the buckets. Understood?
Ma'am, but for the bucket 1, reorganization was required. No, we added one bucket, then now Srinivasan has gone into the another bucket, removed from the first bucket. So this
Yeah, which,
reorganization will have to do. So that is overhead, no?
yeah, that is an overhead. For every step you, once you extend a bit, the entire thing will be reorganized. Right, because the entire hash bucket address table has to change according to that.
Okay, ma'am.
That overhead you have to do. Okay, the
So it's
main
like,
thing why dynamic hashing is better is because less collisions are going to be there, less chaining is going to be there.
okay.
Okay, now if I want to insert gold and LZ records, what is gold from which department? Physics. Now we are working with how many bit prefix? Right now 2-bit. So physics 2-bit prefix is 10. So it will try to go into the 10 bucket. But this is also already filled. So now we will do what? Extend one more bit. Right? So I take the first 3 bits. Now will I extend this 3-bit for just this gold record or every record in the 10 bucket? Where did the collision occur? In 10 bucket, this one.
Yes, ma'am.
For which record did the collision occur? Gold. Gold is from physics department. So I had to extend one more bit. So physics department 3-bit value is prefix is 100. Sorry. 100 prefix. Same 3-bit extension you have to do for the records in this 10 bucket that are already present. Why? So that we can find that which 2 records are matching and who can belong in this bucket and who I can cast in a separate bucket. So what are the records here? Einstein, who also belongs from physics. So he will also have the same 3-bit prefix. But for finance, if I find 3-bit prefix, what is it? 101. So which 2 records will come in the same bucket?
Physics.
Only
Einstein and
Einstein
gold.
and gold.
They will come
Gold.
together. Wu has to go to a different bucket. But now again, since we have extended 1-bit prefix, the entire thing has to be reorganized. So bucket address table will now have how many combinations?
8.
8 combinations. See, this is changed to now 3-bit prefix. So write down the combination 000001 010 011 100. This is just to understand better. Okay, these are the 8 combinations, right? See, have we found any more records which start with 0 as prefix?
No, no.
So all 4 0 prefixes are still pointing to the first bucket. because this is not yet filled. So whatever comes with a 1-bit 0 prefix, I can enter here. Okay. So all 4 of these are still pointing here. Now physics 3-bit prefix was 100. So Einstein and gold both go into the 100 bucket. This one. Okay. This bucket. This is 100. Wu from finance, what was his 3-bit prefix? Finance 3-bit prefix 101. So he is in the 101 bucket. And Srinivas, okay, LSED. LSED is the next record. LSED is in which department? History. History, what is the, okay, first let's start from 1 bit. Bit 1. Okay, first bit is 1. How many possibilities are there? With 1-bit prefix, 3 different buckets are there. So go to the next bit, 1 1. With 1 1, how many possibilities are there? With first 2 bits as 1 1, how many buckets possibilities are there?
2.
So 110 and 111. Right. Now when we entered Srinivasan in this one, here when we entered Srinivasan, how many bit prefix did we use? 2 bit. Right. Just by taking the first 2 bits, I was able to discern that Srinivasan should be separated from Wu and Einstein. So here also, if you have the first 2 bits as 1 1, you can directly enter in this bucket. No need to check for the third bit. Okay. So for now, you can enter LSED with Srinivasan. Both of them have 1 1. See, that's why both the arrows are pointing here for 1 1, because we don't care about the third bit right now. Third bit can be 0 or 1. Since the first 2 bits match, so they can come together in a bucket. Now when you try to enter CATS record, CATS is from which department? Computer science again. Okay. So computer science, take the first bit, 1. How many possibilities in buckets? 3. Take the second bit, 1 1. So it should come to which bucket?
2.
This bucket. Right. See, these things are the bits. Okay. How many bit prefix we use to identify that these records should go into these buckets. To get the correct buckets for Einstein, Gold, and Wu, we needed to use 3-bit prefixes. So both of these buckets have 3 bits. But to identify the correct bucket for Srinivasan and LSED, we only use the first 2 bits, 1 1. So the size of this bit prefix is 2. Now when you try to enter CATS record, who is also from computer science, just by getting the first 2 bits, you know it should go into this bucket. Right. But is this bucket does this have any more space?
No.
No.
So what do we do?
Extend.
Extend which one? Computer science first. So what are the first 3 bits of CS? 1 1 1. Now is this only enough, or do I need to find 3-bit prefixes for these 2 records also?
Ma'am, for inserting CADs, how now we know that our bucket address table is already on 3 bits prefix. How did we decide only to choose 2 bits to see the bucket for CADs?
Since in bucket address table, both of these addresses are pointing to one bucket.
Okay.
Okay. So we, from the first 2 bits, we identified that it should go into this bucket. But since this bucket is filled, so now we extend 1 bit. Now we take 3-bit prefix.
No, ma'am, but CATS department is computer science. So and that's a new entry that we have to do. Why did we decide that out of this new entries department will take only 2 bits? Why not
because
3 bits now?
We start with 2 bits, right? We start with the first bit, then the second bit. If with first bit we cannot identify, we extend 1 bit. If second bit also we cannot identify, then we extend third bit.
Okay, ma'am. Okay. So we always start from first
1 bit. Yeah, always with 1 bit first start. So here 2 bits gave me this bucket, but this bucket is filled. So I am extending 1 more bit. For CS, the first 3 bits are 1 1 1. Now to find who should stay together and who should go to a separate bucket, we need to find 3-bit values for Srinivasan and LSED also. So Srinivasan is also from CS, so he will also have 111 prefix. History, what is the 3-bit prefix? 110. Right. So now we will create a separate bucket for 110. Okay. Until now, 110 and 111 were both pointing to this bucket. Why? Because the prefix was 2-bit, 1 1. But now we have taken 3-bit prefix, so now there are two combinations, 110, 111. So it divides like this: 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1. So now 110 bucket will contain only the history record for LSET, and Srinivasan and Katz can go together since they're from the same department. Their 3-bit prefix is 111. Now see, every bucket has been using 3-bit prefixes except the Mozart bucket. That still used only 1 bit, that is 0. Right? So all these 4 records or combinations that start with 0 are still pointing to only this bucket. But for 100 there is a separate bucket now, 101 there is a separate bucket, 110 there is a separate bucket, 111 there is a separate bucket. Is it clear till now?
Yes, ma'am.
Next we have to enter Sing. Sing is from finance, right? So finance, first take the first bit, 1. How many possibilities are there? 4 possibilities.
4.
Take the second bit, 1, 0. Now how many possibilities? 2. This and this. So we have to take one more bit, 1, 0, 1. Now which bucket? I can directly point to this bucket. Is there space present? Yes. So we will directly enter Sing here. Okay. Next
So
is
till the time we identify a bucket, we keep increasing the bits to be compared.
Correct. Until we can find a direct entry that okay, this many bits are present in the hash table. So now I can identify the bit bucket directly. Okay, so always start with 1 bit. This is the easiest way of understanding this. Start with 1 bit, then keep extending until you find the proper bucket.
Okay.
So next, when we try to enter Calipari, Calipari is from history again. Start with 1 bit, which is 1. 4 combinations start with 2 bits. Now we are narrowed it down to this and this bucket. So again go to 3 bits, 110. So which bucket should it go? This one, 110. LSET bucket. So Calipari can enter here. Now go for Crick. Crick is from biology department. Biology department first start with 1 bit. What is the first bit? 0. So which bucket is a possibility? This one, Mozart bucket. Right? So I can directly enter Crick here since there is a space. Still it is using 1 bit prefix only to identify. That's why this size will not change. Next, when you go to try brand, okay, brand is from which department? Now see. See, up to now this has been done. Okay, now if I want to add brand is from CS. So start with 1 bit, 2 bit, then in 3 bit you will be able to identify that it should come in this bucket, 111. But we see it is already filled. So usually by practice we should extend 1 more bit. But what we can see is that all the entries are from computer science only. So no matter how many bits I extend, the prefix will not give different prefixes. It will be same for all 3 records. Correct. If I extend 1 bit also, all 3 are from computer science. So they will have the same prefix. I cannot take any 2 into 1 bucket, right? So in this case, we have no other choice but to do a chaining. Okay. So here we will form a chain and enter brand here. Since all 3 are from same department, so no matter how many bit prefix you extend, the prefix will remain same for all 3. So in such cases, you have to do chaining, but dynamic hashing reduces the chances of chaining by a lot. Okay. So out of all these records, only 1 chaining was required. Now if you want to insert Kim record, Kim is from electrical engineering. So what is the first 1 bit prefix of electrical engineering? 0. So it should go to this bucket, right? This bucket, but this bucket is now filled. So what will we do? Extend 1 bit. Can I extend 1 bit? In electrical engineering, if I take 2 bits, it is 0, 1. Similarly, I have to extend 1 bit for both of these Mozart and Crick. So for music, if I take 2 bits, it is 0, 0. Music, 0, 1 for electrical engineering. And for biology, what are the first 2 bits? 0, 0. So which two should come together? Biology and music.
Music.
Right? So in the next table, see music and biology. So Mozart and Crick will stay together. Okay. And Kim will go to a separate bucket. So what are the prefixes? 00 bucket is this. So both these entries, see 00001, which start with 00 prefixes, will point to this bucket. And the bucket in which electrical engineering is entered, 01. So what are the possible prefixes? 010, 011. Both of these will point to electrical engineering bucket, this one. That's why I write the prefix so that you don't get confused. Okay. So now we have entered every record. Now you ask any doubt you have. This is difficult to understand. See, easiest way to do this type of problems is always start with one bit, no matter what. Okay. Every time you are inserting a new search key, start with one bit. Then you will have the possible combinations key. Okay, these buckets I can enter it in. So then extend one more bit. So every time you extend a bit, your sample space becomes smaller. Okay, your number of possibilities becomes smaller. So until you reach one bucket possibility, you keep on extending the bits. Okay, and hash prefix, this hash address table or the bucket address table will contain the number of combinations that are suggested by the highest number of prefix that you have used till now. So since we have used 3-bit prefixes, so there are 8 possible combinations. Even though we haven't used all the different combinations yet, we can use them if we need them. Clear? Dynamic
Yes,
hashing
ma'am.
is... Anyone has any doubts? Please ask.
Ma'am, I have one doubt, ma'am. Doubt in the sense a question. See, we right now entered so many records in this hash structure, right?
Right.
This sort of a question will come in our exam like this?
Yes, this type of question has come before. Okay. So what will be given to you is the actual table like this instructor table. So some table will be given, these hash values will be given. So we might not give you 32-bit, we might give you 16-bit values. Okay. So the options will be like this, that after entering all the search keys, what should the structure look like? How many buckets should be there? Each bucket should contain what records? Each of the options will be one such structure. You have to find the correct structure. So for that, you have to perform the hashing. We'll give you the hash function. Sorry, here's no hash function. We'll give you these hash values. Okay. Based on that, you have to enter in all the records in the correct buckets and then match with the options.
Ma'am, the first thing that comes to my mind is, first of all, getting all this into the question in that small terminal. That's the first.
Yeah, it is difficult, but I created one.
The second thing that comes to my mind is, right now, the system, the center, every year, every term, it is becoming smaller and smaller. Now the desk size has become so small that I can't even keep my paper and write. Either I have to bring the keyboard up and then I have to keep the paper and write. So that's
okay.
The level.
These are the TCS centers you're saying?
Yes, ma'am. And imagine getting a question like this and going up and down in terms of a terminal and again in the paper. And this time around, we had a beautiful center where we were against the wall and there was no place for anybody to go behind us. But still people had to go either to give paper or to receive paper or to go for the restroom. Then everybody had to get out of the chair, come to the side, and then give way for the others to go. All this in between while writing the exam, ma'am.
Okay, I'm not aware about this. So what you can do is just, if this is since this sounds like a genuine issue, so you just write one mail. Okay, write one mail to me. Okay, put me on the mail and put you sir as CC. Okay.
Okay, sir. Okay, ma'am.
So I will forward this to the actual committee so that we can do something about this.
Thank you, ma'am.
Okay.
Ma'am, terminal means what the other student was saying. I didn't understand. I have to write in the terminal.
The actual portal. Okay, the exam portal. Okay. So this type of...
No, we have to solve on rough paper, no?
Yeah, you have to solve on rough paper and you have to then give the answer in the actual portal, right? So this type of question, it takes a lot of time to solve. and it is a lot of work to solve such questions. So if the conditions are already difficult for you, so test conditions should be ideal. So yeah, definitely this is some issue we should bring up. So you send me that mail, I'll forward it to the committee. Okay.
Thank you, ma'am.
Yeah.
Ma'am,
But
our TCS centers are good. I mean, the space constraint is not like that severe as what I think
yeah, in some
Ms.
states
Ramya has
it's
brought
good.
out.
Yeah,
But
some states it's not good.
very small and little tricky issues are uh, students are writing on the monitors and all. So maybe when Miss Ramya is writing to you, if she can write that clean desk and clean monitors are not there. There is so
Okay.
much marking on the monitor, you
On
can't
the monitor
differentiate.
itself.
Monitor itself, it's not center's fault, ma'am. It's the student. But
Like with pen they have written on the screen.
yes, ma'am. A lot of pen marks are there on the screen, and my screen was totally blue with the markings. Maybe people are trying to, judge by the pen and work out the answer there itself, not by writing per se, but maybe by
Yeah, but marks.
pointing.
Okay.
Huh?
Yeah. Yeah.
So
See, all of these issues. See, whoever has center related issues or exam condition related issues. Okay, you can always mail us. We will give that to the committee, and they will discuss to get new centers. Okay. Don't shut these issues down. You send me the mails. Okay. Whoever has issues.
yes,
Thank you,
ma'am.
ma'am.
But good part was the thesis manager switched my PC. But
Yeah, they
along with that,
usually try to do that, but
huh,
still, see, it's already you are under a lot of pressure because of exam. These issues are not required, right?
correct. So
So, see, this type of question usually, previously we did not used to give questions from dynamic hashing since it's difficult, like you said, that to even form the structure of such questions is very difficult in the TCS backend portal. Everything we have to configure. But I have created questions on dynamic hashing which we did give in previous papers. Okay, and students could solve it because we had such sessions where I solved this type of problems. So
this is a
in the
good
end
topic,
term,
ma'am. We should have actually question
it
on
is
this.
because see, in
It's,
a real life scenario, dynamic hashing is the one that we use more. Okay, and
I
in
have one
end,
doubt.
yeah.
Ma'am, when do we decide to use the chain? Like, we could have increased hash prefix also.
See, if you increase hash prefix, what is our goal here? What is the search key? Department name, right? That means we want all department names in the same bucket. All the same department names should come in the same bucket. That's the goal. That's hashing. Whatever is the search key, every unique search key should go to a unique bucket, right? If there are multiple search keys which are having the same value, like here 3 people have computer science as their search key, so they all should belong to the same bucket. Okay, ideally.
Okay.
Okay,
Got it
so
now.
like this, so since here no matter how many bits I extend, all of them will have the same prefix. That's why we use chaining. Okay.
Okay.
Now in the end term revision session, I have 2 more questions of dynamic hashing which I'll discuss. Okay, I'll give them to you beforehand so you can solve yourself. Then I'll discuss it in end term. Okay, I hope this is clear for
yes,
everyone.
ma'am.
If you have any more doubts, you can ask. Otherwise, so what is left from your week 9 is just that B3, B plus 3 and bitmap indices. Okay, so whoever takes the next session, you tell them this. I will also try to inform. Okay, so bitmap index, B3, B plus 3. Only this part is left. Okay, do you want me to share this PDF with you?
Yeah, please.
Ma'am, this is extract of our slides only, I think. No?
Extract of slides only. I have just taken the
Okay.
important ones. Okay, so if you want the annotations, I can give you the PDF.
Okay, ma'am.
Okay, all right. Yeah, thanks for joining, everyone. Please join the
Ma'am.
Saturday class also.
Yeah. Thank you, ma'am.
Yeah, thanks. Yeah.
Ma'am, how did you make the 0011 table, like binary table? Up.
See, these are just prefixes, right? So the entire code that is given to you, these 32-bit prefixes, these are all binary codes, right? So if I take 3 bits, then how many possible binary combinations are there? 2 power 3. What are those? So these are the 8 combinations. If you take 2 bits, there are 4 combinations possible. This is just binary. Okay, if you take 4 bits, 16 binary combinations are possible. So how do we form these combinations that you are asking?
Yeah.
So for 1 bit, see, this is very easy. For 1 bit, what is possible? 0 and 1. Correct? For 2 bit, okay. For 2 bit, if I start with 0, okay, what can be the next bit? 2 possibilities, either 1 or 0. Or if I start with 1, the next bit could be 0 or 1. So what are the possibilities? Either 0 0 or 0 1 or 1 0 or 1 1. Similarly, now if you place a third bit, okay, so then what happens when you place 0 as the first bit? Here you can have 1 or 0, here also you can have 1 or 0. So what are the possible combinations? 0 0 0, 0 0 1, 0 1 0, 0 1 1. Just find the combination. Similarly for 1 also, 3 bits, you can have anything here. So write all the possible values: 1 0 0, 1 0 1, 1 1 0, 1 1 1. Okay. Usually in exam we won't give you greater than we won't give you such problems where you'll have to use more than 3 bit prefix. Okay. All right, so I'll stop it here. Yeah, thanks for joining.
Thank you, ma'am.